So we skip chapter 6.3 and go straight to 6.4 to look at the chemical phosphorus removal. But we can still scroll back a little bit to this plant layout here, which shows a typical flow diagram for a physical chemical treatment plant. And that is similar to what you will be seeing at the wastewater treatment plant. First, you have some type of grit removal. That's the first thing we'll see. And that's essentially to take out garbage. But at the local plant, they have this in two steps. First, they have a bar screen, and then they have a grit removal unit that you will see. They both stink real bad, but there is good ventilation, so it's not too bad being there. Then comes the kind of chemical treatment. And here you see the rapid mix and flocculation. This you will see. And then we have sedimentation. At this treatment plant, the sedimentation are long rectangular basins. So we'll look at that. And after that, in the local plant, it just goes straight to the fjord. While here they illustrate a more advanced treatment where they may have a more sensitive recipient, for instance, a small stream or a local lake, then you need some extra treatment. And sometimes you have to add some, call it alkalinity, or just because the chemical precipitation removes everything, and then it can be not so good for the next treatment steps. But here you also see the filtration, similar to the drinking water plant, where you can use sand filters, for instance. And in this case, they really want to polish it, so they use activated carbon to take out remnants of unwanted chemicals, maybe medication and stuff like that. At the local treatment plant, the sludge is just taken to thickener and to dewatering, and then to anaerobic digestion. Actually, anaerobic digestion, I guess you could say, comes in between here at that plant, and then there is further centrifuge before they have a fairly dry product that is taken out to the field. And for each of these two steps, there is reject water being brought back to the inlet of the plant, just like in this drawing. Part of our research, we have two master students during their thesis work, is can we treat this reject water in such a way that it causes less disturbance to the coagulation process? Because that is an issue on most of these plants, is you treat the sludge only during working hours when people are there. Because running centrifuges and stuff with nobody around, that's dangerous. That means you have this extra, quite strong water, reject water, coming from these two lines, going back into the inlet at the same time as you have the peak load during the day. And that can cause significant disturbances to your coagulation process. So we have a nice research project where we're looking into biological treatment here to make the whole system with the coagulation work better. So in a sense, what we're doing is we're trying to improve the chemical coagulation process by adding a little bit of biology on two of the side streams. This is something that we've been doing master's study projects on for a few years, and now we have a Research Council sponsored project to further develop this concept. But back to the topic, the main reason for adding the coagulant at the treatment plant here, and I would say probably every other wastewater treatment plant in Norway, is to remove particles and phosphorus. So phosphorus removal is what drives this focus on coagulant. Very strict discharge limits for phosphorus, and the assumption is if you handle the phosphorus very carefully, make sure it's very low. You also remove most of the BOD, because most of the BOD, most of the organics are actually particles. There are some dissolved that will go through this way, but with particles removed, these treatment plants actually manage to be within the discharge limit for organic matter without running a main biological process, which is very common, like activated sludge around the world. So only the largest treatment plants in Norway, in central areas like Oslo, have a full-fledged biological treatment. Along the coast, where we have good recipient, it's generally considered good enough to do the coagulation. But as I said, the disturbance here makes it more challenging to reach the discharge limit of both phosphorus and organics. So that's part of our research. But let's go back now to the phosphorus removal theory, which we find in 6.4. And the main chemicals used, we have already mentioned some of them, and also here is a list of the factors affecting how to implement it that you can read on your own. Phosphate removal with aluminium and iron, that's by far the most common. But as you will see, calcium can also be used, and it is used in a few cases. But here we see the basic chemistry. Dissolved alum react with dissolved phosphate, turning it into aluminum phosphate that precipitates out efficiently. And it does so together with the particles, so it's easy to remove in the sedimentation. Same with iron, reacting with phosphate, just 1-to-1 molar basis in both cases. So based on this, it looks like a rather easy and trivial case to determine how much alum do you need if you know how much phosphate is coming in and how much you want to remove. However, there is a lot higher demand for these chemicals than what you see from these equations, because remember, they're also involved in removing all the particles. So they're involved in charge neutralization and bridging between particles. So the amount that we can calculate straight from the phosphate balance is much less than what you actually need. So if you only add that, you will only add a fraction of the phosphate and a fraction of the particles. And again, you can work as much as you want on theory, but you really need to do experiments. Jar test, again, very useful, as you will be seeing in the lab. And it's highlighted here also. Unfortunately, the reactions are deceptively simple and generally do not apply. So why theory when it doesn't apply? Well, it is because it is the chemistry that happens, at least at a superficial level, but it's only a small part of the story. So therefore, we will not go deeper into the chemistry, but we'll just scroll through it and look at, yes, it's much more complicated. There are also reactions with other ions. So these precipitation also consumes alkalinity, which is something we don't really want even, but it happens. And it creates even more sludge in the end. And also then, especially if you have a biological process downstream, there may not be enough alkalinity. For instance, if you want nitrification. As we've seen, nitrification consumes alkalinity. So this is something that many treatment plants are struggling with, how to find the right balance here. Some places they actually buy extra alkalinity to add for the downstream nitrification. So, but then it becomes quite expensive. I also mentioned that phosphate can be removed with calcium, and some plants do it. It used to be much more popular. It could perhaps come back. And the reason is, even though it's a bit more expensive and does have some other problems, you end up with calcium phosphate, which is a much nicer form of phosphate if you want to recycle it into fertilizers. So for instance, when Yara make their mineral fertilizer, they buy fossil calcium phosphate. We could make calcium phosphate directly from wastewater. Of course, it would be full of other contaminants, so it's not obvious that Yara can use it, but at least it's easier than iron phosphate, which they certainly cannot use. So there are many things going on these days that can change this perspective a bit. But let's take a little bit closer look again at these types of diagrams, where we have the concentration, where we want, when we add a chemical, we need it to be dissolved. When it's precipitated, we want it to be solid. So again, we see we need to be in a very low pH to when we add the iron, in this case. But then immediately when it mixed with the water, the pH of the water, the wastewater, with its buffer, it will be immediately brought into the range where iron phosphate is precipitated out as a solid. So that's what we're always aiming for, obtaining that with a minimum of chemical use and minimal of mechanical complexity. All right, now here's a little bit about calcium phosphate, and you see here is a calcium phosphate you can get by coagulation. But that's not where we want to go. We want to go in and do a bit more real estimates of chemical requirements for phosphate removal. But let's make that into a new video and stop this one here.